law, and specifically the manipulation problems for Hess's law. So in Hess's law, we can either do product minus reactant reactions and figure out what the delta H is, or the energy either per mole of a reaction, by using the thermochemical chart. But sometimes you don't have all of the substances that you need for the reaction on the chart. You can't find them on the chart. And so what you're going to do instead is you're going to use reactions, and we're going to add up these reactions to try to figure out what our total is. And so it could be a little bit confusing. It sounds a little bit confusing, but once we go through some of these, it should make a lot of sense as to what the goal is in here. So it says most reactions occur in a series of steps. So it may be impossible for you to determine the heat of a reaction directly. Hess's law is going to help us figure this out indirectly. So we're not actually doing this, performing this reaction, and figuring out how much energy was released or how much energy was absorbed, because maybe we can't do it in a calorimeter. Maybe there's no mode for us to be able to figure out the energy. It's something that is happening outside of the realm of our lab, of what we can do in the lab. So for example, changing carbon from diamond to graphite takes millions of years for that to happen, because the reaction is so slow. So Hess's law provides a way to calculate what the heat of the reaction is by adding the thermochemical equations together to give the final amount. So if you sat there and waited and waited and waited for diamond to form, what's wrong with that?
It's going to take a while.
Yeah, you're going to die, and then other people are going to come along, and then they'll die, and other people will come along, and they'll die, and millions of years later, you'll have your diamond.
So eventually someone's going to get that.
So maybe you could get that energy at some point. So what we're going to do is we're going to add these thermochemical equations together. And this is also called Hess's law of heat summation. It says if you find it necessary to reverse a reaction, what do you think happens to your delta H if you have to reverse a reaction? You probably also have to reverse the sign. Awesome. Then delta H should also be reversed. In other words, positive becomes negative and negative becomes positive. Okay? So Hess's law states if a reaction is the sum of a series of reactions, then delta H is the sum of all of your delta H's. Okay? So we're going to calculate the delta H for this reaction using products minus reactants, and then we're going to convert graphite into diamond. It's nice that on this one, we actually do have the reaction. We can use our thermo chart in order to figure this out. So let's do it that way. So what we want is, I want you to take a look on your thermo chart, and I want you to find carbon in the graphite form and carbon in the diamond form. Okay? So we're going from graphite to diamonds. Okay, so what we're doing is we're going from carbon solid in the graphite form to carbon solid in the diamond form. What is the value in the graphite form?
0.
0. What's the value in the diamond form?
1.8.
1.88. And what units is this?
Kilojoules.
Kilojoules per mole. Good. And it is a mole, so that works. That's kilojoules per mole. So that's 1.88. So how do you figure out the delta H for this? You do products minus reactants. So you would just do 1.88 minus 0, which means our answer is just products minus reactants. So positive 1.88 minus 0 is just positive 1.88 kilojoules. Okay? So now we're going to do this the other way, and I'm going to show you how this works to get the same answer, but now doing it using the manipulation way. Okay? Because a lot of times you won't have them both found. Okay? So here's what we're going to do. First, I'm going to write my sum line. So I have my two reactions. I'm going to rewrite them down here. So I'll have an A and a B right here. And I'm going to do a sum line right down at the bottom. And I'm going to write what I want my final reaction to be. My final reaction is that one right there. It's carbon solid in the graphite form, forming carbon solid in the diamond form. So that's what I want. That's my overall target reaction. Typically, it'll be bolded for you. That reaction will be bolded in the problem. These are called the intermediates. And the intermediates are what we're going to use to try to manipulate so that we get this as our answer. And everything will end up canceling out. So let me talk to you a little bit about how things cancel out. If you have things on the reactant side and on the product side, then they basically are canceling out. Because you have if you have a 1-to-1 ratio of them. If you have 2 on a reactant side and 1 on the product side, you can cancel the 1 on the product side and be left with how many on the reactant side? 1. Okay? So you can cancel out between the reactants and the products, even if they're on different lines. So what I'm going to do is I'm going to try to find something in each line that matches my target. And I use shapes, okay? So different people do this differently. What I do is I use shapes, and then I attach that shape to the one that's in my target. So here in this line, what is the only thing that also appears in my target equation? Yep, which one? The graphite. Awesome. So I'm just going to put a star there, and I'm going to put a star right there. And then I'm going to compare two things. I want to compare the coefficient, and I want to compare the side that it's on. If it's on the reactant side, but it's supposed to be on the product side, guess what you do to it? Yeah, flip it, reverse it. Reverse your reaction, but then you have to reverse your sign, okay? If it has the wrong coefficient in it, multiply or divide by that number so that you can get those to be the same. So do I need to do anything to this? Well, let's check the coefficient. Are the coefficients the same? Yes. Are they on the correct side? Well, that's on the reactant side, and this is on the reactant side. So do I need to change anything on this? No. I'm just going to put a 0 with a slash through it. Because after we do these first two, you will not need to rewrite these. You can just do this. As long as you know you're getting the right answer, then you're fine. Okay? So I'm going to rewrite this. Carbon solid graphite plus O2 yields CO2 gas. Line 2. Which one in this line, line B, do I have in my target equation? The diamond. Okay, that's the only one that appears. So let's do, it doesn't matter, a square. I'm going to do a square there, and I'm going to do a square on this one. Okay, so I'm going to do a square on both of those. Check the coefficient. How's my coefficient?
Good.
Good. 1, 1. What about the side that it's on?
Different.
Different. This is on the reactants, this is on the products. I want this to match my target. So what I'm going to do is I'm going to write that I'm reversing this. Okay, I'm just going to write rev. You can write flipped, you can write rev, whatever it is that you want to write on there. Then what I'm going to do is once I'm done with this, I'm going to reverse this reaction. So it's going to be CO2 gas, then my arrow. I like to line up my arrows. That way I know what side, what's on my reactant side and what's on my product side. Yields the carbon solid diamond plus O2. Okay. Does anything cancel out? Yes. What? What do you see that cancels out? The O2. Awesome. Right there, that cancels out with that one. Even though they're on different lines, they're on opposite sides, reactant and product. Anything else that cancels out? CO2 gas. Awesome. Those two cancel out. And what we're left with is our target equation. And if you do this correctly, you don't even have to do this check. As long as you figured out one from each line, then you should be all set to go. You shouldn't even need to do the check for it, okay? So now let's use the numbers for this also. So on here, this first one is supposed to be a negative 393.5 on here. Okay, so this one is negative 393.5 originally. And before I reverse it, this one is a negative 395.38 for this one here, if we do the CO2 minus that. Negative 395.38. Okay. So that's what the values would have been. You would typically are given these values. Sometimes you have to do the calculation for it. So we would have done CO2 minus carbon graphite and CO2 minus carbon diamond to figure that out, but it could be given to you either way.
Wait, Mr. Joe,
Yes.
why aren't you using the O2?
When we subtracted,
Oh, it's 0. Oh, sorry.
O2 0. Yep,
Yeah.
O2 is 0. So you would just do this one minus that one and this one minus that one to get those two numbers.
Okay, alright, thank you.
Did I just switch one of these? That's negative. They're both negative. Okay, good. All right. So now, if we do this part, did I change anything in my top line? No. So that's just negative 393.5. And in my second line, we said we were going to reverse it. So what would you do there?
Positive.
Positive 395.38. Guess what you do to these numbers if it's called Hess's law of heat summation? Add them. Awesome. We're going to add these two together, and that's our overall delta H. So if you add these two together, what you end up getting is positive 1.88 kilojoules, which is what we got over here when we did products to reactants for carbon. Okay, so you can either do it using the chart, which usually you'll be able to use the chart, but if not, that's where Hess's law of manipulation comes in, and you obviously need to know how to do the manipulation ones. So let's try this next one. And this next one has 4 different steps. This diboron is a highly reactive boron hydride, and it was once considered as rocket fuel for the U.S. space program. Calculate the delta H for the synthesis of boron from its elements according to the equation. So here's our equation. That's our target. Okay? So what we're going to do is we're going to do a sum line down here. And this is the last one we're going to do this way, because from now on, you can do manipulation just by figuring out. I'll do it that way first, and then we'll do the check. Maybe we'll do it that way. So here's our final 2 boron solid plus 3 H2 gas, and my arrow B2H6 gas, and I'm looking for the delta H of this entire reaction. Okay, let's do the top line first. So anything in the top line that appears in my target. 2B solid. Good. 2B solid or 2B gas. That is the question. Just kidding. Okay. All right. So I see it right there and right there. How's my coefficient? Good. How's the side it's on? Good. Guess what you do to this line? Nothing. Don't do anything to it. No change. Let's do the second line. Is there something that you see in this line B that matches down here? B2H6. So let's do a square maybe. And then I'm going to put a square down in this one. Okay? And how's our coefficient? Good. What about the side? Wrong. So we need to reverse this one. Let's reverse that. Next line. Do you see anything that exists in this equation and in this equation? H2 gas. Awesome. You want to make sure it doesn't exist anywhere else, because it can throw it off. It can actually cancel it out. So I want to make sure that I don't see H2 gas anywhere else, and I don't. Okay? Otherwise, you want to save it for last. So H2 gas looks good. Let's use a circle on this one. So H2 gas is right there. How's my coefficient? What do I need to do? Multiply by 3. But if you multiply this by 3, you also have to multiply the delta H by 3. You have to multiply everything by 3. So it's going to be times 3 for all of this. So it's going to be a 3, a 3, a 3, and then this one I'm also going to multiply by 3. Okay, so you have to multiply everything by 3. How's the side that it's on? Good. Don't change the side. So we're good with that. We don't have to reverse it. So don't forget you have to check 2 things, okay? Last one. Water is a liquid to water is a gas. Is there water down in this equation? No. What does that mean? If they gave it to you as part of the thermochemical equation, it's one of the intermediates, it's got to be there, okay? But if it doesn't show up in my final one, then where is it? It cancels out. Awesome. It cancels out. So what we need to do is we need to make sure that it can cancel out. How do things cancel out? They have to be on opposite sides. Awesome. So I want water as a liquid if it's on this side. I want water as a liquid to be on the opposite side. If I've got water as a gas, I want it to be on the opposite side. Is that the case here? Kind of. I'm seeing this. Why? Why kind of? Where's my other water as a liquid?
Oh, it's on the other side above it.
It's in line C, right there.
Yeah.
Am I reversing this reaction? No. So it's on the left and that one's on the right. Awesome. Okay? Let's check this one. Water is a gas. Where's my water as a gas?
Line C is the reaction.
It's in line B. Good. It's on the product side, but it's actually a reverse reaction. So this would actually be on this side. Okay, so I'm actually good with my side then, yes? Because if we want it to cancel out, I want them to be opposite, and they are. That's there. This one is opposite of that one because that would have been on this side if we wrote it out, okay? But there's one other thing we need to check. So we just checked the side of it, so the side of it's fine. What about the coefficient? What do you need it to be? 3. Times 3. Why times 3? Because the other ones are. This one, we said we were going to have to multiply by 3. And this one is already multiplied by 3. That we're just reversing. So that means that this line, we also need to multiply by 3, 3, and times 3. Okay, but don't change the side because we do want it to cancel out. So now all we're going to do is we're going to make the change that we said we were going to make. So the first one is negative 1273. If you reverse the second one, then what do you get? Positive, awesome, 2035. This one's times 3, which I have as negative 858. And the bottom one times 3 is positive 132. And guess what you do to these numbers now? Add them. Awesome. So we're going to add all of these together. When we add these together, we get positive 36. And what are the units of this? Kilojoules. Nice. Okay, endothermic or exothermic then? Endothermic. Let's make sure that worked. Okay? So we're just going to check it just to make sure that everything worked. Because you may be looking at that and going, wait a minute, I don't think that's going to work right. So we're going to rewrite everything. So the top line, line A, we are not changing. 2B solid plus 3 halves O2 gas. Yields, don't forget to line up your arrows. Okay, B2O3 solid. That's my first line. Second line, reverse it. So B2O3 solid plus 3H2O gas yields, I'm lining up my arrows, B2H6 gas plus 3O2 gas. Third line, times 3. So 3H2 gas plus 3 halves O2 gas, because 3 times a half is 3 halves, yes, yields 3H2O gas. Last line, D, I'm not doing anything but multiplying it by 3. 3H2O liquid, arrow, line up your arrows, 3H2O gas.
Wait, for C it's 3H2O liquid for the last one.
3H2O liquid, thank you. 3H2O liquid, awesome. Okay, so now what cancels out? So do you see anything that is the same on both sides that we can cancel out? The oxygens? Okay, they're on the same side. Here, how much do you have? 3 halves and 3 halves. When you add 3 halves plus 3 halves, what do you get?
3.
6 halves, which is 3. Good. And how many oxygens do you have on this side? 3. So guess what you can do to those? Cross them off. Those are the same. Again, 3 halves plus 3 halves is 6 halves, which is 3. And that's 3 on the opposite side. What else cancels out? The H2O, the 3 H2O is a gas there, and the H2O is a gas there. And then we have the H2O is a liquid there, and the H2O is a liquid there. What else? One more thing. The B2O3 solid with the B2O3 solid. And everything else that you're left with should be in your final equation, which if we look down, it is. So we did that correctly. Okay? That's Hess's law of heat summation. Fun? I love this. This is so much fun. Yes, question.
So technically, for any of these problems, we could just go to the sheet that has like the numbers and just do it the other way, or
Usually you could, but we're not going to, if it's a Hess's law problem, you're going to use manipulation. If it's a manipulation problem, I'm going to tell you, show your manipulation on certain ones. Or I try to give you ones that are not exact, like I don't give you the same delta H values, and that way I know that you're trying it, that you're doing it the proper way. Question?
Can we just do like the math, like how you did on the right, or do we have to show it all?
Yes, you can just do this.
Okay.
This is your check. This is if you need to check yourself, okay? This is only for checking. This is what you need to show me. And your final answer. That's it. Got it? Okay, so let's go to, so I wanted to show you just the difference between the allotropes of carbon too. So we have diamond here, and then this is showing graphite. And just to show you the difference between what diamond looks like and graphite looks like from an atomic view. So what's the only element that makes up diamond and graphite? Carbon. Okay? And you can see on here that in the diamond form, each carbon is connected to 4 other carbon atoms. And so you can see that they're covalently bonded. What does covalent bond mean? They're sharing what? Electrons. Awesome. So they're sharing their outer electrons, and that's a bond that ends up existing between all of these, okay? So each one has 1, 2, 3, 4 other carbons that it's attached to, that it's connected to. How's graphite different? What's in between the layers? Empty space. We have just IMFs that are in between here, weak forces that are IMFs that are in between here. The covalent bonds are within one chain has covalent bonds, but in between are IMFs. And that's why there's such a difference between graphite and diamond. Even though they're both made of carbon, one of them is connected covalently between every single carbon atom, and then the other one has just forces in between. Gummy bear sacrifice we're going to do later on, so we'll come back to that. All right, so the enthalpy, or H, of a reaction is the, let's see if you remember this, let's try to do this together. It's the energy absorbed or released.
And the formation.
Energy absorbed or released. Now, for a reaction, I'm going to tell you there's no F on there, so we're just going to say for a reaction. And there's a difference between a delta HF. You can have a delta H COMB. What do you think that's for? COMB, and it's not for combing your hair.
Combination.
Combustion. Yeah, combustion. You can have a delta H of combustion. You can have a delta H for a whole bunch of different things. They'll have fusion and fission, and they'll have formation, so solidification. You can have different delta HF values. And delta H is simply the energy absorbed or released for any reaction, depending on what that reaction is. If it's an F, then it's for formation. It represents the change in energy of the system, where the balanced reaction moves in the direction, something. For example, the balanced reaction, yours probably says it on here, moves in the direction, okay, good. So in the direction written. For example, the balanced reaction of H2 and O2 to form water is written as follows. And I'm going to show you this reaction. We're going to do this together. So it does provide a big explosion, so I'll show you that later on also. This reaction has an enthalpy of negative 259 kilojoules. That is, if it's negative, then what does it do to the 259 kilojoules? It releases it. It releases 259 kilojoules of energy. So here. Switch colors. Okay, if this is red. If the reaction, so it's exothermic. If the reaction were reversed and we were interested in splitting water molecules, but you could use what type of instrumentation to split water? Starts with an E. Electrolysis. Awesome. Electrolysis. Into their individual elements, it would have an H equal to what? Not negative 259, but positive 259 kilojoules. Awesome. That is, it would absorb or require 259 kilojoules of energy from the surrounding environment to break those bonds, so it's an endothermic reaction. In many reactions, the process of the reaction is not as straightforward as a balanced equation written. So we said that we were going to use intermediate reactions. And this just sums up what we did. So we're not going to go through all of this, but just in summary here. So it says, Hess's law states, the overall enthalpy change for a reaction is equal to the, what do you have to do to it? Sum, perfect. The sum for the individual steps in the reaction. All you're doing is you're summing up all of those intermediates. That's all you're doing. The sum for the individual steps in the reaction. That's all it is. That means if the intermediate reactions are known, the enthalpies of each intermediate reaction can be what together? Added. Nice. Added together to find the enthalpy of the original. So this just tells you what to do. It just says, like, what are you looking for? How are you doing this process? Multiply by a side, and then when you're done, the very last step is adding. So let's do this. Methanol, also known as wood alcohol, used to be obtained by heating wood without air present, and so now it's prepared by the hydrogenation of carbon monoxide at 400 degrees Celsius. So we're going to use methanol, and I'm going to show you the big jug of fun today. It's also used in the synthesis of plastics, fibers, and adhesive, and can also be used as motor fuel. So let's write the equation for the combustion of methanol. So do you remember the formula for methanol? CH4 would be methane, good. So what do? 3 OH. Awesome. Take one of the hydrogens off, make it an OH. If it's combusting, what are we adding it to? O2. Yields.
Carbon
Nice. CO2 and H2O. Awesome. Let's balance it. So I've got one carbon. Here I have 4 hydrogens, and here I have 2. So let's make this a 2. And now let's check our oxygens. Here I have 1 plus 2 is 3, and on this side I have 2 plus 2 is 4. What's the best thing to do? Change the odd to even. So let's change that to a 2. Now that gives me 2 carbons, so I'm going to change this and make that 2 carbons. My hydrogens just changed, so instead of having 4, I have 4 times 2, which now I have 8 hydrogens on there. Sorry, so 4 is what I need on there, because now I have 8 hydrogens. Okay, so now let's do our oxygens. I have 2 right there, plus another 2 is 4, and here I have 4 plus another 4 is 8. So if I say that that's 4 and 4 is 8, minus the 2 there, how many do I have? 6. So how do I make that a 6? 3. A 3. Perfect. Okay, so that's my balanced equation for it. So now let's figure out what our delta H is going to be, okay, for this reaction. What form do you think this methanol is going to be in? Typically it's dissolved. Usually they have it dissolved in some water. So either it'll be liquid or it'll be an aqueous where they've added some water to it too. So depends. It depends on how you purchase it. So I'll tell you too. What do you think the oxygen is? Gas. The CO2? Gas. And typically water would be a liquid. But in the case of combustion, usually in the case of combustion, how does water end up, what ends up happening to the water? It ends up vaporizing, so usually it ends up vaporizing. We're going to do it as a liquid because you'll see at the end of the reaction that we do get liquid. It cools down and it does form liquid, and we can spill that out. Okay, and then let's do this. Now what's going to happen is, typically you get this in a liquid or an aqueous form, but in order to burn it, what needs to be true of it? And I don't know if you've seen this on the outside of containers. It'll say something like highly flammable, but what's highly flammable? The vapors. Awesome. The vapors are highly flammable. So what do you think this needs to be then? What are we actually burning? The gas. Nice. We're actually going to burn the gas. Okay. So what I want you to do is we're going to do a product minus reactant for this one because we can. Everything's on the chart, so we can figure out what that is. So let's write down what our values are for each one of these. Oxygen we know is what? 0. Good. Okay, so that one's 0. And let's see if we can figure these out. So CH3OH gas, let's take a look at the thermo chart.
Negative 201.2.
Perfect, negative 201.2. Negative 201.2. Okay, CO2 gas. Negative 393.5. And H2O is a liquid. Negative 385.83. 285.83. Thank you, sorry. 285.83. Multiply by your coefficient, don't forget. Okay? So I'm circling my coefficient so that we multiply by it. So go ahead and do products minus reactants. I want you to try this one in your calculator for sure because we usually only have one product, so make sure you add your products and then subtract your reactant from it, okay? So go ahead and try that. And I do parentheses in one step, so I don't write anything else down. I would do parentheses, 2 times that, plus parentheses, that multiplied, minus parentheses, 2 times that. So go ahead and plug that in and tell me what you get. Is it negative 15?
Yeah, 1527.9, yeah.
Okay, good. Anybody else? What are you getting? Negative 15, 27, so negative like 1528. So for this, the delta H is equal to negative 15. I have 28, negative 1528 kilojoules, which means that this reaction is very exothermic. Okay? It's highly exothermic. What if I asked you this is for the reaction. This is the delta H for the reaction. What if I asked you for the delta H for per mole delta H per mole of CH3OH? Question mark. What if I wanted it per mole of CH3OH? What would you do then?
Put it over 2.
Why divide it by 2 or multiply it by 2? Divide. Why would you divide it by 2?
There's 2 moles in it.
Perfect. This reaction is for 2 moles of CH3OH. But if we only want it for 1 mole of CH3OH, then what we're going to do is we're going to divide this number, negative 1528, and you can either do it as a bridge problem. You can say that it's that many kilojoules for 1 mole, but then say for 2 moles of CH3OH, what is it? So it's negative 1528 kilojoules for 1 mole. So for 2 moles, then I want to divide it by 2. And so what we end up getting is negative 764 kilojoules per mole of CH3OH. I could not say per mole there. It could be per 4 moles of water, okay, or per 3 moles of oxygen. So just making sure that we do that correctly. Question?
I'm kind of confused why you use the total, like delta H, just to find that. Why didn't you use the negative 201.2 and divide that by 2? Because isn't that just the CH3OH?
So I want to know what the delta H for this reaction is per mole. So that is not the delta H for the reaction. That's the heat of formation. That was a great question. So I want to make sure that you understand the difference. This is heat of a reaction. And so if I want to know how much energy is released for every mole of methanol that I have, then that's what I'm using. Heat of formation is different because heat of formation is, everybody say it with me, either the energy absorbed or released for the formation of 1 mole from its elements in their standard states. That's not what this is. That number is the heat of formation of CH3OH. Okay, question?
Is delta H reaction only for combustion reactions or
Nope.
for anything?
It's for anything. Delta H, just delta H is for any reaction, but then you could specify it. You could say delta H of combustion. So this could actually be called delta H of COMB, of combustion.
If it's not just a combustion reaction, will they tell you what they want you to find the delta H for?
Yes,
Okay.
yeah, and if they just say delta H, then that's just a general anything. It can be any reaction, just
Yeah.
delta H for any reaction. Okay, excellent. So what we're going to do is, let's just do the manipulation piece. So this is your overall reaction. Do you see something in line 1 that matches over there?
O2.
The O2. Why would I not use the O2 though?
Because it's in both.
It's in more than one place. Don't use it if it's in more than one place, okay? So what isn't in more than one place that only appears in the final? The NO. Good. So I'm going to, you can even like cloud it. So I'm going to put a cloud around this one and a cloud around this one. So what do I need to do to it? Is it on the correct side? Yes. What about my coefficient? What do I need to do? Divide by 2. Awesome. I need to divide this one by 2. Let's look at the second line. What appears only in this top reaction? N2. Awesome. So I'm just going to box this one here, and I'm going to box this one there. And is it on the correct side? No. So I know I need to reverse it. And what about my coefficient? Divide by 2 again. Good. Reverse and divide by 2. So let's divide this one by 2, and what we end up getting is negative 306.5. And the second one, we need to divide it by 2 and reverse it. So when I divide it by 2, I get 395. So what's my answer?
Negative.
It's negative there, right? So positive 395. What do I do to these two numbers? Add them up. Good. And the answer ends up being a positive 88.5. And what are my units? Kilojoules. Awesome. Okay. So that's how you're going to do the Hess's law stuff. And then when we come back, we'll do calorimetry, and we'll talk about a bond calorimeter and how to do the calorimetry problems, and then we're done with notes. Okay. Great job, everyone. That's Hess's law.